Now let's take a look at the excited state of the helium atom. How do we make excited states? Promote electrons. So we started off with 1s squared. Now let's promote one of those electrons to the 2s so that we have a 1s, 2s configuration for the excited state of helium. Still, we're going to write a total wave function, spatial part times spin part. The electrons have to be indistinguishable, overall antisymmetric with respect to exchange. Let's write the spatial part. The spatial part, right, we're going to have a 1s electron and a 2s electron. But again, we don't know which one is electron 1 and which one's electron 2 because they're indistinguishable. So we're going to have to either write that as a plus or a minus combination. Where we always put an electron in the 1s and one electron in a 2s orbital. Plus or minus combinations, they've got to be normalized. So if we have normalized them, we also have to multiply them by 1 over the square root of 2 to normalize those. And again, we're going to get a symmetric and an antisymmetric combination with either the plus or minus sign. We had symmetric and antisymmetric spin functions. We've got now, for the excited state, symmetric and antisymmetric spatial parts. We still have to put them together so that they're overall antisymmetric. Therefore, right, this symmetric part can get only put together with the antisymmetric spin part. All right, so we're going to get one total wave function, right? That's going to be the symmetric spatial part times an antisymmetric, down there, right? I'll just represent that with a minus. So there's going to be one and only way, one way we can do that. So we could call this the singlet spin part, right? We've got spin of 0, and that corresponds to 2s plus 1 equals 1. We'll call that a singlet. Up here, we had s equals 1. That corresponds to 2s plus 1 equals 3. That's a triplet, a set of triplet states, right? And we call this, the 2s plus 1, that's the spin multiplicity. It keeps track of how many spin functions there are, right? So for the symmetric part, there are 3 that go together. That's a triplet. For the anti-symmetric part, there's only 1. That's a singlet. We see that, yes, there's one way to write this, right? That is total antisymmetric overall. It's the symmetric spatial part, and there's an anti-symmetric spatial part, right? If we take the symmetric part, we got to pair it with an anti-symmetric spin part. That's a singlet state. Then there are 3 ways to write total wave functions that are a combination of a spatial part that was anti-symmetric with the appropriate got to multiply these by the appropriate. There are three different ways to write the appropriate spin part because we can use that triplet. And that's how we'll get the total antisymmetric wave function, multiplying an antisymmetric spatial part with a symmetric spin part. Notice something about these three here, right? That if we look at the case where the two electrons are at the same place, that will go to 0. That is, the two electrons naturally avoid each other. In the case where the spins are the same, the electrons avoid each other. So there's some degree of electron correlation in this triplet set of states. Here, the electrons are avoiding each other. Therefore, the electrons avoid each other. If they have the same spin. This we call Pauli repulsion. Right? The electrons are avoiding each other because they're trying to go into the same space and have the same spin. What's that going to do? It's going to lower the electrostatic repulsion between those, and therefore the triplet state is going to be lower. This set of triplets states is going to be lower in energy than the singlet state. So this is a general rule. For a given electron configuration, when you can make both triplet and singlet states, the triplet's going to be lower in energy because the electrons naturally avoid each other. This isn't electrostatic repulsion. This is because they have the same quantum numbers. They're going to stay away from each other. Same spin, they avoid each other. So that's just naturally baked in correlation. It doesn't happen when the spins are opposite, but it does happen when the spins are the same.